Okay, so general accuracy is not doing our work justice. It is not giving you the tools as a data scientist to be able to go to your boss and have a productive conversation. So one way to better assess the performance of a classification model is to use what we call a confusion matrix. And basically what we're going to do, we're going to divide our data into 4 quadrants. It's the same 10,000 points, but we're going to divide them into 4 quadrants that represent different levels of accuracy. Okay, so in a confusion matrix, the columns are the ground truth, the actually observed. And so one column is the actually observed negative examples and the actually observed positive examples. In the rows, we have the predicted negative examples and the predicted positive examples. So now that gives us 4 quadrants. And let's go through each quadrant now. So let's start with the uppermost left quadrant. That's called the true positives quadrant. That's where our algorithm predicted that users will default, and those were the actual users that defaulted in the real data. Right? So ideally, we would want every single person that defaulted to be predicted as having defaulted. Now, if you go diagonally from that, you have what's called the true negative quadrant. And those are the people that we predicted will not default, and they did not default in actuality. Right? So a perfect model would put the counts of those two in the diagonal, and 100% of our use cases would be in these 2 quadrants. But unfortunately, no model is perfect. Which brings us now to the topmost right corner, which is the false positives quadrant. And those are the examples that the algorithm classified as going to default, but they actually didn't default, right? Opposite of that, in the lower left quadrant, those are the false negative examples. And those are the customers that we said are going to default, but actually didn't. Okay, so let's look at how we classified these 10,000 test samples. So let's assume that we classified 81 customers as true positives, meaning the algorithm predicted that they are going to default, and they actually did. So that's our true positive quadrant. Next, let's assume that the algorithm predicted that 9,644 customers were not going to default, and indeed they didn't. Those are our true positive classifications. Next, let's look at our false positives, right? These are the customers that we said are going to default, but they actually didn't. Let's assume those were 23 customers, right? And finally, that leaves us with our false negatives, right? In this case, these are the people that we said are not going to default, but actually defaulted. And let's assume those were 252 customers. And so that makes our confusion matrix. But what I want you to pay special attention to are the false positive and the false negative instances. So let's go back to our example. We said that about 252 customers were deemed that they are safe, that they are credit-worthy people by our algorithm. Yet, it turns out that in the ground truth data, they did default, right? And that's a serious business risk, right? Imagine if I lended this person $50 million thinking that they are credit-worthy or loan-worthy, right? But then the business lost $50 million. If you work in the financial services, usually they bake defaults into their business margin. So they know that X% of accounts are going to default. That's just part of the business practices. But nonetheless, it is extremely important for you to communicate this risk to your business, because these are the kinds of nuances that will come back to bite you if you just report the accuracy alone. And then we have the other side, which are the false positives, right? In this case, we said that 23 members or 23 applicants, right, are going to default, but in reality, they didn't. And this is a missed business opportunity. So I might have missed out on several millions of dollars of loans that I could have handed out because my algorithm was too cautious, if you will. And so the idea is, how do we find this balance? How can we alter our algorithm so the samples that are in the false positive and false negative quadrants gently shift into the true positive and true negative quadrants? That's the goal of the work. Unfortunately, there's always a trade-off. There is no way to get a perfect diagonal where all your samples are in the true positives and the true negatives, because that would be wonderful. But so you, as a data scientist, you need to learn the art of data science here. And how do you balance basically your business needs with the statistical accuracy of your model to provide value to your organization?